Welcome to the Explainer. Today, we are unpacking one of the most fascinating and frankly frustrating dilemmas in modern renewable energy. Meet the hero of our story, the organic solar subcell. This incredibly thin, highly tunable material is an absolute powerhouse when it comes to efficiency. But as you'll see, it's also incredibly fragile. We're going to unpack the fascinating science of why these cells are so efficient, exactly how they manage to literally destroy themselves, and the ingenious sort of superhero team-up engineering required to save them. Okay, let's dive right into this. Here is our roadmap for today. First, we'll look at the organic solar breakthrough. Second, the quantum bandgap penalty. Third, stopping the unmixing process. Fourth, death by sunlight. Sounds dramatic, I know. And finally, the tandem shield solution. All right, part one, the organic solar breakthrough. To really understand where we are today, we have to look at this massive paradigm shift from older, restrictive fullerene-based setups to something entirely new. For the longest time, single-junction organic photovoltaics, or OPVs, relied heavily on fullerene acceptors. But honestly, they were stuck. They just couldn't push power conversion efficiencies past that 10% mark. But then, a massive breakthrough happened with the development of non-fullerene acceptors, or NFAs. Specifically, these really unique low bandgap molecules, like the Y6 molecule developed back in 2019. These NFAs basically unlock the ability to harvest near-infrared light. That single leap pushed standalone organic cells up to a staggering 20.42% efficiency. And, as we're going to see later, it perfectly set the stage for monolithic tandems to hit an incredible 26%. So what's the secret sauce here? Well, NFAs completely transformed these thin-film materials into highly specialized, narrow bandgap near-infrared harvesters. In plain English, their whole job became catching as much of that invisible, near-infrared light from the sun as physically possible. And to do that, scientists had to squeeze the organic absorber's bandgap as much as they could. But here's the central conflict of our story. Pushing that bandgap narrower and narrower to catch more light comes with a very steep, very fundamental thermodynamic cost. Which brings us to part two, the quantum bandgap penalty. Now, what's really interesting about this is that we're stepping out of pure materials engineering and right into the strict, unforgiving laws of quantum thermodynamics. In the race to maximize near-infrared harvesting, researchers kept shrinking the bandgap. But meta-analyses revealed this massive, invisible brick wall right at 1.3 electron volts. When the acceptor bandgap drops below this exact mark, all the performance metrics just mysteriously crash. It completely defies what standard, ideal theoretical models would predict. So why does 1.3 eV act as this absolute danger zone? The culprit is a heavy piece of quantum physics called the Engelmann-Jortner energy gap law. To put it simply, imagine the energy states inside your solar cell as two distinct floors in a building. When you shrink the energy gap to catch more light, you're essentially lowering the ceiling and raising the floor, bringing them closer together. When they get too close, specifically below that 1.3 eV mark, the quantum vibrations of those states literally start crashing into each other. Their wave functions exponentially overlap. So instead of that trapped solar energy cleanly flowing out to power your house, it just bleeds away as non-radiative recombination. It just turns into useless heat. It's basically a massive quantum short circuit. So what does this invisible quantum crashing actually look like in the real world? Well, you get a massive voltage deficit, it severely suppresses the charge collection efficiency, and you see this progressive drop in both the fill factor and the short circuit current. Basically, all of this represents the first major vulnerability our organic cell faces. It's a harsh thermodynamic punishment for trying to be just a little too efficient at harvesting infrared light. Let's move to part three, stopping the unmixing process. Now, quantum physics isn't our only enemy here. We also have to tackle morphological stability. In other words, how do we stop the cell from physically destroying itself from the inside out? You see, the operational longevity of these organic cells relies entirely on the physical blend of their materials at the nanoscale. According to the Flory-Huggins theory, when the internal enthalpic driving forces in an NFA blend are too high, the materials actively want to separate over time. It's exactly like a bottle of oil and vinegar dressing. You can shake it up to mix it perfectly, but if you just let it sit there, it inevitably separates. In a solar cell, when the donor and acceptor domains separate and crystallize, it completely wrecks the intricate electrical pathways, creating localized traps and ruining the cell's ability to actually transport charge. So, how do we stop the oil and water from separating? Researchers came up with a really brilliant fix, a ternary blending strategy. By introducing a minor fraction, just about a 20% slice of fullerene derivatives into the mix, it acts like a structural glue. These fullerenes suppress the excessive growth of the NFA domains, essentially locking the materials permanently in place. This guarantees those critical electron pathways remain totally stable, finally bridging the gap between high initial lab efficiency and actual commercial-grade durability. All right, part 4, death by sunlight. Okay, so we've solved the quantum short circuit and we fixed the structural unmixing. But that brings us to what is easily the greatest irony in this entire explainer. The source material puts it bluntly. High-energy illumination accelerates structural degradation even under completely inert testing conditions. Think about what that actually means for a second. You can take this highly efficient organic solar cell, place it in a perfect vacuum, completely shielded from oxygen and moisture, and the raw, unattenuated power of the full solar spectrum will still physically tear it apart. The very thing it desperately needs to generate power is actually its third major villain. And this brilliantly illustrates how the sunlight murders the cell in two very distinct ways. First, we have ultraviolet cleavage. High-energy UV photons act like microscopic molecular scissors. They directly photooxidize and literally cleave the NFA framework, permanently destroying the cell's light harvesting capacity. Then you have visible torsional strain. Photons in the visible spectrum act more like a medieval torture rack. They cause this dihedral twisting along the polymer donor backbone, which induces high energetic disorder and dramatically accelerates those heat losses we talked about earlier. So, this leaves us with a seemingly impossible dilemma, right? Our organic cell is an absolute master at harvesting near-infrared light, but UV and visible light actively destroy it. So, how in the world do we protect our fragile hero without blocking the exact light it needs to generate power? Part 5, the tandem shield solution. The answer is all about teamwork, specifically a monolithic 2T tandem configuration. The most elegant way to protect the organic cell is simply to put a shield in front of it, but not just a dumb piece of glass. Engineers placed a wide bandgap perovskite solar cell right on top of the organic one. Think of this perovskite layer as a pair of power-generating sunglasses. Step 1, it perfectly absorbs all that high-energy, destructive UV invisible light. Step 2, instead of just blocking it, it uses that intense light to generate its own massive amount of electricity. Step 3, the organic bottom cell, sitting safely underneath, receives only the benign, low-energy, near-infrared light. It gets exactly what it is perfectly tuned to harvest, without getting destroyed in the process. And the results of this optoelectronic synergy? They are absolutely astounding. A standalone organic cell is great at near-infrared absorption, maxing out around 20.42%, but as we know, it suffers rapid degradation. But when you combine it into a monolithic tandem OPV, the whole setup harvests the entire full spectrum. The top cell takes the harsh UV and visible, the bottom takes the gentle near-infrared. This teamwork skyrockets the total max efficiency to nearly 26%. And because the organic cell is finally shielded from those damaging wavelengths, its operational lifespan jumps to well over 5,000 hours. It completely neutralizes those primary high-energy degradation mechanisms. So why does all this complex chemistry and quantum physics actually matter to you and me? Well, the ultimate goal here is next-generation building-integrated photovoltaics. Because these organic solar cells can be made highly tunable, incredibly thin, and even semi-transparent, they are the absolute key to creating solar-generating windows and smart building facades. Solving these quantum penalties and chemical and mixing annoyances means we can actually build transparent materials that survive in the real world for years and years. We've really journeyed a long way today, from the fragile nature of organic cells, down into the quantum traps of the Engelmann-Gertner law, through the chemical battle of unmixing, and finally to this brilliant, power-generating perovskite shield that ultimately saves the day. With organic perovskite tandems now breaking that 26% efficiency barrier and proving they can actually survive the elements, how long until literally every window in your city is a silent power generator? It's a hugely fascinating future to look forward to. Thanks so much for joining me for this explainer, and I encourage you to look a little closer at the windows around you. They might just be the power plants of tomorrow.